Hi and welcome to this Leaving Cert Higher Level Probability Exam Questions video. So today we're going to look at a variety of exam questions broken down by topic. This is very much linked to the review video. If you haven't already looked at the review video, I've linked it down in the description below. You can use that to give you an idea of what you need to know about the questions, and this video is then going to go through the examples themselves. Example 4.1, probability using sets. Two events A and B are such that the probability of A is 0.33, the probability of B is 0.45, and the probability of A intersection B is 0.13. Find the probability of A union B, the probability that either A or B occurs. So I'm going to use a Venn diagram. I think it's the most straightforward way to really see what's happening, but I will show you the formula as well. So our intersection is 0.13. So you always fill in your Venn diagrams from the intersection. They told us that was P, the probability of A intersection B. The probability of A is 0.33, but we already have 0.13 in here, so that is 0.2. Remember, probability of A is the probability of the full circle. That's our 0.33. And then 0.45, again, we have 0.13 there, so that is 0.32. What I would always do at this point is also figure out what is left in the universal set, so that is not in set A or set B, so 0.65. No, apologies. So when you add them, you get 0.65, and take it away from 1, you're actually going to get 0.35. So what is the probability of A union B? So here we have A union B, and we can work that out by adding everything in A and B. So 0.2 plus 0.13 plus 0.32, and when you add them, you get 0.65, or if you prefer, 13/20. Now, there is a formula you can use, and that is the probability of A union B is equal to the probability of A plus the probability of B. Now, if we were to add those two circles, the problem is the intersection is double counted. So we need to take out the intersection to make sure that that double counting disappears. So that is a formula we have in the probability section, and it is not in the log tables. We have one formula from probability that is in the log tables, and that is the binomial or Bernoulli Trials. So make sure you know all your formula. Find the conditional probability probability of A complement given B complement. So I'm going to give you just a general formula for conditional. So that's A given B is equal to the probability of A and B. So that's intersection all over the probability of B. So that is probability of B, another formula that you need to know. So I'm just making sure we're very clear about the formulas that you need. Now, this is obviously a little bit different because it's the probability of A complement given B complement. That means the probability of A complement intersection B complement all over the probability of B complement. So what that means is, complement means the opposite. So A complement is everything that is not A. So that is the 0.32 and the 0.35, and everything that is not B. So actually that basically is everything that's not in the circle. So not A intersection not B is basically not A or B. Not B is going to be 0.2 plus 0.35. So that is the piece of A that is not in B and also the bit outside. So that is 0.35 all over 0.55, and that simplifies down to 7/11. You can write it as a decimal, but you are going to be a lot more accurate if we can leave it in fractional form. State whether the events A and B are independent. So this is the formula for independence. So events are said to be independent if the probability of A multiplied by the probability of B is equal to the probability of A and B, or probability of A intersection B. So this is another formula, again, you need to know off by heart. So that's our independent formula. So we need to know that off by heart. So we can either use that when they tell us they are independent, or we can figure out if events are independent. So probability of A, on my right color pen, probability of A times the probability of B. Does that give us the probability of A intersection B? Let's check it out. So we get 0.33. This is the whole thing, 0.45. Does that give us 0.13? And when we work it out, this works out as 0.1485. And does that equal 0.13? And the answer is no. So that does not equal, does not equal, does not equal. Therefore, A and B are not independent. And the justification is our sum there on the right. Are not independent. Okay. So part B, event C is such that the probability of C is 0.2. A and C are mutually exclusive, while A and B are B and C are independent. So be careful, and people mix those up quite a bit. That idea of mutually exclusive, so that means no overlap, and independent means one does not affect the other. Now, when they're independent, as we've just seen with the independence formula, there is most definitely an intersection. So you can do this in the traditional three sets where they all intersect, but A and C don't intersect. So what we're going to do for our Venn diagram is just put C here on the end. I'm also going to put a box around it for our universal set. So some things will stay the same. This is the same as before, 0.2, 0.13, but B will change because B and C are independent. That means the probability of B multiplied by the probability of C should give us the probability of B intersection C. So the probability of B was 0.45. The probability of C we've just been given is 0.2. And when we work that out, that gives us 0.09. So that goes in here, 0.09. So what does that leave us in here for B? And that's 0.23. And here in C, 0.11. And working that out, we get 0.24 in our universal set, but not in set A, B, or C. So that's a case where we're using our independence to figure out that intersection. So the next thing is hence, so using this Venn diagram, find the probability of B union C complement. So the probability that B and C do not occur. So that is everything that is not B or C. I'm going to use some highlighter here. So I'm not talking about B and I'm not talking about C. So I'm going to, I kind of only have like really black or dark. So I don't want B and I don't want C. So that only leaves us with 0.2 and 0.24. So that is the probability of B union C complement is equal to 0.2 plus 0.24, which is 0.44. Example 4.2. So some probabilities with algebra. So this is 2019 question, and although quite straightforward, caused a lot of problems for students. One of the main issues was that students weren't able to distinguish between the set difference sign, which is here, and the given, so the conditional probability sign, which is a straight line. So be really clear about this. When we say the probability of F less S, it means the probability of F without S. And you can see, I'll show you what I'm talking about here. We're talking about this one here, and that relates to just this one here. That's nothing got to do with conditional probability. This is set difference. Okay. So everything that they've told us here is given in the Venn diagram. I'm just going to rub these out because I don't particularly want these as I'm working through it if I can get away with it. Okay, so they've told us that F and S are independent. So probability of F multiplied by the probability of S will give us the intersection, because they've told us it is independent. We're not checking independence. And using this fact, we're going to try work out X and Y. So probability of F is a quarter plus a fifth. It's everything. And S is a fifth plus X. And that should equal to a fifth. So we're going to do a little bit of cleanup there. Put that into your calculator and get 9 over 20. I'm going to drop the multiply sign and I'm going to get common denominator. So that's going to be 1 plus 5x over 5. So that's just making a common denominator. And that equals 1 over 5. So multiplying that out, we get 9 plus 45x over 100 equals 1 over 5. Let's multiply both sides by 100 to get rid of the fractions. These cancel. We're left with 9 plus 45x. And then this gives us 20. That gives us 45x equals 11. So x equals 11 over 45. So that is our first answer, 11 over 45. The next thing we want to do is we want to work out y. Now y is a little bit easier, and most students would have been able to do something to figure out y. And basically all my probabilities should add to 1. So a quarter plus a fifth plus x, which is now 11 over 45, plus y, and that should all add to 1. So if I want to add my like terms here, so the ones that are just numbers, what we get is y plus 25 over 36 is equal to 1. So y is equal to 1 minus 25 over 36. So y is equal to 11 over 36. And that is our answer for y. So using some very, very basic knowledge of probabilities and this independence formula, and the fact that everything in the universal set, so all probabilities should add to 1, the probability of something happening for sure, so a certain, is 1. So part B. In a club, there are German, Irish and Spanish children only. There are 10 Spanish children. So I'm going to try set this up in a way that helps me. So I have German, Irish, and we have Spanish. Okay. And there are 10 Spanish students. There are twice as many Irish children as German children. So I don't know what German is. I'm going to call it X. That means there are 2 times that Irish. They're all in a group waiting to get on a swing. One child is selected at random to go first and will not rejoin the group. That's really important. Then a second child is selected at random to go next. The probability that the first child is German, so probability that the first child is German and the second child is not German, is basically equal to a sixth. How many kids are in the club? So what's the probability that the first one is German? Well, we're going to have x over, let's work out the total number here. So that's 10 plus 3x. So there's 10 plus 3x kids in total. So the probability of choosing a German child from this group is x over 10 plus 3x. Multiplied by, now remember we are one less, so there is one child that has already been chosen and is no longer in the group. So now we have 9 plus 3x. That child was German, so that's not affecting our top line because not German means it could be Irish or, and or means plus, Spanish, and that equals to a sixth. And we now have our lovely little algebraic equation which we need to solve. So the top line is x times 2x plus 10 all over 10 plus 3x, 9 plus 3x, and that equals 1 over 6. going to get rid of my fraction, so I'm going to do 6 times x, 2x plus 10 equals 10 plus 3x, 9 plus 3x. And we're going to multiply that out. So 6x by 2, that's 12x squared, plus 60 equals, let's multiply this out. We get 10 times 9 plus 3x plus 3x times 9 plus 3x. This is actually missing an x here, so let's multiply all this out. So we have 12x squared plus 60x is equal to 90 plus 30x plus 27x plus 9x squared. It's quadratic, so we're going to bring everything over to the left hand side. 9x squared plus 60x minus 57x minus 90 equals 0. We get 3x squared plus 3x minus 30 equals 0. Minus 90 equals 0. I'm a step ahead of myself. To equal 0. We're then going to divide across by 3 to simplify the equation. We get x squared plus x minus 30 equals 0. You're going to use guide number or minus b, and we're going to get x equals minus 6 or x equals 5. Now there's only one valid answer, and because x represents the number of children, it can't be negative. So our answer is x equals 5. Now be careful, they did ask us in the question how many children are in the club. So we said the total number of children was 10 plus 3x. So now that we've worked out x, the total is 10 plus 3 times 5, which is 15, which is 25 children. Example 4.3. Probability of a game. Orla and Liam are playing a game that consists of tossing an unbiased coin. The first person to get heads is the winner. Orla tosses first. Find the probability that Liam wins the game on his first toss. So that means Orla will lose. So there's a 1 in 2 chance of winning, but also a 1 in 2 chance of losing. So Orla loses, and always means multiply, Liam wins. So that gives us a 1 in 4 chance. Orla wins the game on her second toss. Well, that means Orla loses and Liam loses and Orla wins, which gives us a 1 in 8 chance. So the next part has a linked sequences in series. So what's the probability that Orla wins the game? So we have to look at all the different ways in which Orla could win the game. So she could win it on her first toss. So that means she's a 1 in 2 chance of winning. Or, and the word or means add, she could win it on her second toss, which you worked out in part 2. That was a 1 in 4 chance. 1 in 8 chance. Or she could win it on her third toss, which will be a 1 in 32 chance. And what we end up with is a geometric sequence. It's a geometric sequence where we have a common ratio of 1 over 4. And we want to add together all of these basically forever, because she could keep losing until the numbers get really big. So the best way, or the only way, where we can actually find the full probability of Orla winning the game, not on any given toss, but the full game, is we're going to do the sum to infinity. So the sum to infinity formula is a over 1 minus or. So we need to figure out a, the first term, which is 1 over 2, and or, which is the common ratio, which is 1 in 4. So we have a half all over 1 minus a quarter. And when we work this out, we get a 2 in 3 chance that is equal to the probability that Orla wins. Now, she has a 2 in 3 chance of winning because she gets to go first. So that means Liam has a 1 in 3 chance of winning. So if you're ever playing a game, something similar to this, the person who goes first will have an advantage. So if you were kind of thinking, oh, it's not fair, you know, that it's not a 50-50 chance of winning, yeah, you will be right. So we have just proven that using our knowledge of probability and sequences and series. A game of chance comprises of a player spinning a lottery wheel, and there are 100 positions in which the ball has an equal chance of landing, but there is only one chance of the player to win. So what is the probability of a single win on a given spin? And that is a 1 in 100 chance. Find the minimum number of spins which Karina must attempt in order that the probability of winning the top prize at least once is no less than 25%. So when we talk about at least once, the best way to work with this is 1 minus the probability that it has never happened. So the probability that it has never happened is the probability of not winning. So we'll do that here. And that is going to be 99 over 100. So it's not just one spin though, it's some number of spins. So let's do a little bit of work here. If I lose on the first one, that's 99 over 100. If I spin a second time, it's going to be 99 over 100 as well. And that can simplify to 99 over 100 squared. If we then go for a third spin, 99 over 100 by 99 over 100, we end up with 99 over 100 to the power of 3. So when there is 2 spins, it's power 2. When it's 3 spins, it's power 3. So when we say n spins, so some number we don't know, we can still use the same logic that it's going to be 99 over 100 to the power of n. And we want that to be no less than 25%. So that means greater than or equal to 25%. Greater than or equal to 0.25. So we're going to write it in decimal, not percentage. So we're going to bring the 1 across, so 99 over 100 to the power of n is greater than or equal to, we're going to subtract 1 from both sides, so we get minus 0.75. We can change our signs, but when we change our signs, we must change the inequality. We're going to need logs to solve that. So what we're going to do to make it just that little bit simpler is we're going to actually work with this as an equation. So let this be 99 over 100 to the power of n equals 0.75. We can then convert that, so we get log to base 99 over 100 of 0.75 equals n. That gives us an n of 28.62. So they asked us for the minimum value. So we're looking for the next, well, the lowest whole number it can be. So the next whole number. So then the minimum number of spins is going to be 29. Example 4.4, combinations and permutations. A jury of 12 people is selected from a panel of 8 men and 8 women. So this is 16 people in total. How many different ways can a jury be selected? So 16, choose 12. And that is 1,820. Find the probability that the jury selected has more women than men. So how many ways can we have more women than men? First, we need to think of the scenario. The first scenario is there could be 7 women and 5 men, or we could have 8 women and 4 men. Now, that's the only 2 scenarios we have, because we can't go any bigger because there's only 8 women, and we can't go any smaller because 6 women and 6 men mean they have the same number. So we could have 7 women and 5 men, which is going to be 8 choose 7, and means multiply, 8 choose 5, or that's a plus, we have 8 women and 4 men. That means 8 choose 8, and means multiply, 8 choose 4. So working that through, this works out as 70 plus 448, which gives us a total of 518. So what is the probability of that? So the probability of that happening is 518 all over 1,820, and that simplifies down to 37 over 130. How many different teams of 15 players can be chosen from a panel of 20 if the captain must be included? Well, if the captain must be included, it just means that instead of a panel of 20, we actually only have 19. And instead of looking for 15 players, we're only looking for 14. So that is 19 choose 14. And when we put that into the calculator, we get 11,628. So what about two players who refuse to be on the same team? So I want to look at a number of scenarios here. So we're going to look at 4 scenarios. So scenario 1, player 1 is on the team. Scenario 2, player 2 is on the team. Scenario 3, neither player is on the team. And scenario 4, both players are on the team. Now, scenario 1, that's fine. Scenario 2, that's fine. Scenario 3, that's fine. Scenario 4 is not. This is the one that is an issue. So this is the one that they won't do. They will not play together on the same team. So instead of working out all of these 3 scenarios, we can say, well, the total number of, so let's work it over here. So the total number of different teams that there could be with no restrictions is just going to be 20 choose 15, which is 20C15, which works out as 15,504. And then if we work out, well, how many scenarios have both of these players? Well, just like we did with the captain, if they're both on it, we only have a panel of 18 and they're both on the team, so we're not choosing 15 players, we're only choosing 13. So that is 18C13, which is 8,568. So then to work out the first 3 scenarios, then all we have to do is say 15,504, so the total number of scenarios, minus the scenario that they're both on the same team, the one we don't want, and that will leave us with 6,936 ways. Okay, so sometimes it's just about approaching these questions in a different way. So if 15 choose or plus 3 is equal to 15 choose 4 or minus 13, find or, given that or plus 3 does not equal 4 or minus 13. So before we actually do this, I want to show you just a little worked example. So I'm going to work with 5. So if we have 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5, and we work those out, we get 1, 5, 10, 10, 5, 1. So 5 choose 0. I have 5 things and I don't want to choose any of them. How many ways can I do that? Well, 1. 5 choose 1. So I have 5 people in a room. I want to choose 1. How many different ways can I do that? 5. 5 choose 2. Although it says 10, there's no kind of special or clever way that happens. It's just coincidence. You can work through with Pascal's triangle to see where these little binomial pieces come from. But I suppose the focus for this question is the fact that we actually have this lovely symmetrical answer. We see this is happening. So we have 10, we have 5, we have 1. And it's interesting because that happens when these 2 bottom numbers add to the top number. So we have 1 and 4 add to 5, so they're symmetrical. And we have 0 and 5 add to 5, so they're symmetrical. And we can use that fact in this particular question because they told us that the 2 bottom pieces are not the same. So these could be maybe the same, but they've told us that they're not. So the only other option is that when you add them together, or plus 3 plus 4 or minus 13, they should add to give you 15. So that gives us 5 or minus 10, and that should give us 15. So 5 or equals 25. So or actually equals 5 by coincidence, like our worked example above. Very simple little question when you understand that idea of symmetry that occurs when you're doing these. These are called a coefficient of the binomial expansion, because we see them when we're doing binomial expansion. But there are combinations, there are choosing. So example 4.5, let's look at some probabilities using these combinations. So in a standard game of poker, each player receives 5 cards, and this is called a hand. The player with the best hand, i.e. the best combination of cards, is the winner. The game is normally played with a pack of 52 cards in 4 suits, and they have given you the cards here. Find the number of possible hands a player can receive. Well, there are 52 cards, and we are going to choose 5 of them. How many different ways can we do that? So that is 52, choose 5. And that is 2,598, 2,598,960. So the best hand is a royal flush, and it consists of a 10, a jack, a queen, a king, and an ace, all of the same suit. Find the probability of a royal flush. So there are 4 royal flush hands because there's one from each suit. So one from each suit. So that means there is 4 out of the 2 million or so, 2.5 million possible hands. So that's 4 over 2,598,960, which then simplifies down to 1 over 649,740. So the next most valuable hand is a straight flush, which is 5 cards in sequential order. That means that they go up. So one after the other. They're all of the same suit, and as part of a straight flush, an ace can rank either above a king or below a 2. List all the ways that a straight flush can be achieved. So let's start with the lowest one. You could get an ace, a 2, a 3, a 4, and a 5. You could get a 2, a 3, a 4, a 5, and a 6. You could get a 3, a 4, 5, a 6, a 7. You could get a 4, a 5, a 6, a 7, and an 8. Get a 5, a 6, a 7, an 8, and a 9. 6, 7, 8, 9, and a 10. Could get a 7, an 8, a 9, a 10, and a jack. Could get an 8, a 9, a 10, a jack, and a queen. Could get a 9, a 10, a jack, a queen, and a king. And just be careful, 10, jack, queen, king, ace is actually not one, because this is actually a royal flush that we dealt with on the last question. So list all the ways that you can get a straight flush. That's the first part of the question. And hence find the probability of a straight flush. Well, okay, so there's 3, 6, 9. So there's 9 straight flushes. Straight flush, I'll say hands in each suit. So that means the total number of straight flush hands you can get is 9 by 4, which is 36. So then to get the probability of a straight flush is going to be 36 over the total number of hands, which is about 2.5 million, 2,598,960, and if you simplify that down, we get 3 over 216,580. So last part of this question is another valuable hand is a full house, which is 3 cards of one denomination and 2 cards of another denomination, e.g. 3 jacks and 2 5s is a full house. Find the probability of a full house as a fraction. So I'm going to use what they've given us as a guide to help us. So how many different ways can we pick 3 jacks? Well, there's 4 jacks, choose 3. But there isn't just jacks to choose from. We have 13 possible cards that is true for. So then we come around to the next one. So we have, for 2s, we have 4 possible 2s and we want to choose 2 of them. And we don't have 13 cards to do this because we've already said that one of them has come first. So imagine the jack has gone. So this is only going to have 12. So the first part says 3 of some card and means multiply, 2 of another card. So that's how many ways it can work. And then that is all going to go over the total number of hands. And that's 960. And when you simplify that down, we should get 6 over 4,165. Example 4.6, expected value. A local sports club is planning to run a weekly lotto. To win the jackpot of €1,000, contestants must match one letter chosen from the 26 letters in the alphabet and 2 numbers chosen in the correct order from the numbers 0 to 9. In this lottery, repetition of numbers is allowed. For example, M33 is an outcome. Calculate the probability that M33 would be a winning outcome in a particular week. So this is just asking us, what is the probability of winning? So the chance of us winning is going to be the chance of us picking the right letter. So there are 26 letters in the alphabet, so we have a 1 in 26 chance. There are 9 digits because we're including 0. So we have a 1, or sorry, there's 10 digits because we're including 0. So we have a 1 in 10 chance of picking the right number and another 1 in 10 chance of picking the right number again. So we get the right letter and we get the right number and we get the right number again. So the probability of winning this is 1 over 2,600. If a contestant matches the letter only, the letter and one number, but not both numbers, because both numbers means that they've won the jackpot, they'll win €50. Using the table below or otherwise, find out how much the club should expect to make or lose on each play. Correct the nearest cent. So the jackpot is €1,000. If you match the first letter, you get 50. If you match a letter and the number, so letter and first number, letter and second number, or letter on its own, if you fail to win, you win nothing. So the chance of winning is 1 over 2,600. So then we need to figure out, well, what's the probability of matching the letter and the first number? So that's going to be 1 over 26, match the first number, and then we don't match the second number. So that's 9 over 10. So that gives us a 9 over 2,600. 2,600. And we should get exactly the same answer here for the second number because all we're doing is flipping where that 1 over 10 and 9 over 10 is. So that gives us 9 over 2,600. So 9 over 2,600. So what's the chance of getting the letter and neither number? So that's the letter. Oh, go again, 26. But not this number and not this number. So that's 81 over 2,600. And when we do that, we're left with only figuring out one other probability. And that is the probability you fail to win. Now, there's 2 ways to do that. The only way you fail to win is if you don't match the letter. So that works out as 25 over 26. And effectively, it doesn't matter what happens with the numbers, so you can choose any number. So that's 10 over 10. If you match the numbers, it doesn't matter. So that just works out as 25 over 26. Another way you could do that, all the probabilities should add to 1. So if you add all these together and subtract them from 1, you'll get 25 over 26 as well. So the next thing we want to do is we're going to multiply x by the probability of x. This is going to be in numbers. I'm going to do it either as fractions or decimal places. Money should be 2 decimal places, but I'm going to give an extra one so we don't have an effect of rounding too early on. I'm stuck for space, which is why I'm going to use decimal. But if you use fraction, that's absolutely perfect. 5, 5, 8, and then that is 0. So what I want to work out is the expected value. So the expected value, the sum of x times the probability of x. So that is when you add all these numbers together. So when we do that, we get 2.29, and this gives us the expected payout. So expected payout, so how much they will expect to pay out. Now, they only charge €2 per play, but they're basically paying out $2.29 each time somebody plays. So that means that there will be a loss of 29¢ per play. Now, does that mean they lose 29¢ every time someone plays? No, it just means if we were talking about huge numbers, so if somebody was playing again and again and again, and we were talking about millions and millions of people playing, it would work out on average that they would lose 29¢ per play. When we talk about these expected values, expected payouts, they're not what actually happens, but more what will happen on average in the long run. The club estimates that the average number of plays per week will be 845, and the club wants to make an average profit of €600 per week. How much should the club charge per play? Correct the nearest cent. Okay, so let's go back. The expected payout for each play is from part 1 229, and that's per play. You can work this by making it bigger, but I'm going to break everything down by per play. So they want to make a profit of €600, but let's break that down as a profit per play. So how much do they want to make every time somebody plays? Well, they want to make €600, and they're estimating that that is between 845 plays. What that means is they want to make about 71¢ per play. So if they have to pay out, so this is, the payout. So if they want to pay out $2.29 per play, plus make a profit of 71¢, what we have is they should charge $2.29 plus 0.71¢. So we have, this is the payout plus the profit, and that means that they should be charging €3 per play. Example 4.7, probability tree diagrams. Blood tests are sometimes used to indicate if a person has a particular disease. Sometimes such tests give an incorrect result, either indicating the person has the disease when they do not, that's called a false positive, or indicating that they do not have the disease when they do, which is called a false negative. It is estimated that 0.3% of a large population have a particular disease. Now that is given to us on our probability tree diagram here. A test developed to detect the disease gives a false positive 4% of the time. That means if you do not have the disease, it tells you you do. So this actually goes in here on our tree diagram. That one's already there. And it gives false negative 1% of the time. So that is given here. A person picked at random is tested for the disease. What is the probability associated with each branch of the tree? So write the probability associated with each branch of the tree in the blank boxes. So each branch should add up to 1. So we get 0.997 in here, 0.99 in here, 0.96 here, and then to work out the final box, it's going to be multiplying 0.003 by 0.99, and that works out as 0.00297. Here we get 0.003 times 0.01. That's 0.00003. Here we have 0.997 times 0.04, and that gives us 0.03988. And finally, we have 0.997 times 0.96, and we get 0.95712. Hence, or otherwise, calculate the probability that the person selected at random from the population tests positive. So they might have the disease and test positive, or they might not have the disease and still test positive. So that is scenario 1, they have the disease and test positive, or, so has the disease and test positive, that's 0.00297, or, so or means add, they do not have the disease and test positive, so that's 0.0398H. And that gives us the probability that somebody tests positive for the disease is equal to 0.04285. So a person tests positive for the disease. What's the probability that the person actually has the disease? So what we're being asked is the probability that a person has the disease given they test positive. So this is actually a conditional probability. So we're going to just work with the conditional probability formula. Remember, this is not in the log tables. You need to know this off by heart. Probability of A given B is the probability of A and B all over the probability of B. And we're going to highlight all this. And if we think about what we have in terms of A and B, so say that's A and B, what is the probability that you have the disease and test positive? So go up to this tree diagram, have the disease and test positive, that's this number here. So we have 0.00297 all over the probability of B, the probability that you test positive, which we've just worked out, that's 0.04285, which works out for us as 0.0693. And just to help us with the next part, I'm going to write this as a percentage. It's about 6.93%. The health authorities consider using a test on the general population with the view to treatment of the disease. Based on your results, do you think people of tests be an effective way to do so? Give a reason for your answer. So just bear in mind what we've just worked out is if you test positive, there are two options. The first option is that you have the disease, and the second option is you do not have the disease. And we've just worked out, well, the probability of you having the disease if you test positive is about 7-ish%, so 6.93. That means the chance you don't have the disease is 93%. That's huge. So it's more worrying this piece here. So if you were going to use this for treatment, that would mean, and I suppose this is the best way to describe it, no, this is not effective. For every 100 people treated, so who get the treatment, only 7 will have the disease. So you've 93 people taking whatever are taking on this treatment that don't need it. Only 7 will have the disease. That's really bad. But it is very good example of where maybe on the very top level the numbers look good. Yeah, statistically there was nothing terribly wrong with all those probabilities, and only as we delve a little bit deeper do we then start to understand, well, actually this is an issue. And these are the kind of calculations that they would do, the FDA in America and other bodies in the EU, to make sure that drugs and treatments are safe and effective. You know, this idea that 93 people out of every 100 will be treated incorrectly, that's awful. So it's really good to have an understanding of these issues around probabilities and statistics. Example 4.8, Bernoulli Trials. A certain basketball player scores 60% of free throws in the shot she attempts during a particular game. She gets 6 free throws. What assumptions must be made in order to regard this as a sequence of Bernoulli trials? So the things that they didn't tell us that we would have to assume, well, that each trial is independent. So trials are independent. They don't affect each other. Now, is that always true? We've seen examples of similar questions where they are not independent, where if you miss one, the probability you get the next one is a little bit lower. So that might be more realistic, but because all they've told us is we want to treat this as a Bernoulli trial, we'll want to assume that the trials are independent. And that is also linked to kind of the second one. It's the probability of success doesn't change, so it's the same each time. Of success is the same each time. There are other assumptions of, well, there's other, sorry, now we'll get this down, same each time. There are other assumptions of a Bernoulli trial, but we're not going to assume them here because we were told. So there are two outcomes. So free throw, is that really an assumption that there are two outcomes? You scored and you miss it? No, I suppose it would be accepted, and that there's a finite number of throws. We don't need to assume that because she gets 6 free throws. That is a finite number. Based on such assumptions, find correct 3 decimal places, the probability that she scores on exactly 4 of the 6 shots. So this is the one formula that we have in the log tables for probability. So if you go to your log tables, it's up in the statistical section of it. It's page 33. So this is the one formula that you do not need to know off by heart. And the formula is n choose or, p to the power of or, q to the power of n minus or, where n is the number of trials, 6, or is the number of successes. And you can define success as whatever you want. So this is going to be making the shot. So then what is the probability of that success? So they've told us that she scores 60%. So we're going to say that's 0.6. And then q is the probability of failure. So 1 minus p, so 0.4. So we get 6 choose 4, 0.6 to the power of 4, 0.4 to the power of 2. This can then go into your calculator, and remember we want these to 3 decimal places, 0.311. So the next one, it asks us, she scores for the second time on the 5th shot. So this is not exactly Bernoulli, but we can split it into 2 pieces. So we have 4 shots here, and we then have the 5th shot. So whatever we do, this is an and. And they've said to us she scores for the second time. So this is a score. And that means in here is a Bernoulli trial where she scores once. So we break this down into 2 sections. So this is n equals 4, or equals 1, p equals 0.6, q equals 0.4, and it is 4 choose 1, 0.6 to the power of 1, 0.4 to the power of 3. And what's the chance that she scores? That's just 0.6. So we have to take that last shot out of it. So when we work that through, that gives us a total of 0.09216. But remember, we're doing 3 decimal places. So that is 0.0. I've actually drawn my line in my wrong place. I'll do it in red. It should be here. And 0.092. Example 4.9, probabilities using statistics. So we're going to get into kind of a more statistical probability in this question before we move on to probability, or before we move on to statistics in the next chapter. So a random variable x follows a normal distribution with mean 60 and standard deviation 5. Find the probability that x is less than or equal to 68. So we're going to use our standardizing formula, and the standardizing formula is in your log tables, and basically what it does is it takes any number which is it's from a set of normally distributed variables, and it will convert it to a standard normal z-score, which basically means we can use our tables. So we have our mean here, which is mu, our standard deviation, which is sigma, and our x here. So z is equal to 68 minus 60 all over 5, and that gives us a z-score of 1.6. So we started off with the probability that x was less than or equal to 68. That's the same thing as the probability that the z-score is less than or equal to 1.6 because we standardized that 68, and we go to our tables and we look that up and we get 0.9452, which is in percentage terms 94.52%, and that's our probability. Find the probability that x is between 52 and 68. So we've done the 68 part, so we need to figure out a z-score less than or equal to z, less than or equal to, above 68 we got 1.6. So we're going to do our our standardizing formula again. Our x is 52, mu is 60, over standard deviation is 5, and this works out as minus 1.6. So we get minus 1.6. To split that up, we get the probability that z is less than or equal to 1.6 minus the probability that z is less than or equal to minus 1.6. And working that through, we get the probability that z is less than or equal to 1.6 minus 1 minus the probability that z is less than or equal to 1.6. If we get that, we have from above 0.9452 minus 1 minus 0.9452, and that works out as 0.8904, which is 89.04%. So part B, the distribution of hourly earnings of all employees in Ireland in October 2009 is shown on this diagram. It can be seen that this distribution is positively skewed. So we're talking about a distribution that is not normal, so we can't use our z-scores. They told us some information. They told us the mean, which was 2205, the median, which is 1782, the standard deviation is 10.64. The lower quartile is 12.80 and the upper quartile is 26.05. So what they want us to do is, if 6 employees are selected from random from this population, what is the probability that exactly 4 of them have hourly earnings more than 1280? So this is actually a binomial Bernoulli Trials. So we have n is 6, r is 4, and we want to figure out what is p and q for this. The formula is n choose r, p to the power of r, q to the power of n minus r. So in order to work out the actual probabilities, we need to go to this idea of, imagine this is my data set, and at the very bottom we have a 0. We have then in the middle our median. Our median is 2205. We then have our top, so that's about 80. Then about a quarter of the way through the data, we have what's called Q1, and that is our lower quartile, and that is 1280. And up here, 3/4 way through, we get Q2, or Q3, which is our upper quartile, which is 2605. So what is the probability that exactly 4 of them have hourly earnings more than 1280? So what's the probability that you earn more than 1280? Well, 1280 is our lower quartile, so that means 25% is here, and that means 75% must be above that. So we're going to say that P is 0.75, Q is 0.25, and then we do 6, choose 4. P is 0.75 to the power of 4 times 0.25 to the power of 2. And that works out as 2966625.